Ashton Grossman. I'm a first year BME student, and this is my Lab 1 on constant velocity. So I'll start this presentation by talking about what the lab is about, and then I'll go over the main physics and ideas and equations that are behind this that you need that are necessary. And after that, I'll explain how I collected my data, how I built the computational model, and then I'll compare the results and wrap everything up with a couple of conclusions. So for this experiment, I analyzed one-dimensional motion at constant velocity, and I tracked the motion using Tracker to get position versus time, and then I created a computation model and GlowScript to predict what the motion should look like. The main idea here is that constant velocity means zero acceleration, and if acceleration is zero, Newton's second law tells us that the net force on the object also has to be zero. Just to quickly review the physics behind this, Newton's first law says that an object keeps doing what it's doing unless a net force acts on it. So if nothing is unbalanced or is pushing or pulling, the motion will also not change. Newton's second law says that force equals mass times acceleration. So if the acceleration is zero, that means the net force is zero, given that the mass is a constant number. And that is likely not zero in this case because we were using a marker. And yeah, these are the key connections to this lab that create a constant velocity. So here's the main results. We have both our computation model and our experimental data. And as you can see, both lines are basically straight, which tells me that the velocity stayed constant. And since the model lines up really closely with the experimental data, that supports the idea that assuming zero net force was a good approximation for this motion, and that there's no acceleration. Also, the systems that we analyzed were rolling a marker, the rolling marker itself, and the surroundings include the table, the air, and the earth. The earth provides the gravity, the table provides the normal force and possibly friction acting in the opposite direction of its motion, and the air may provide a small amount of air resistance. And I measured position using Tracker, and I predicted the position using GlowScript by creating with the code, and then I compared both data sets on a position versus time graph. So for the experimental procedure, I first recorded the marker rolling at a steady speed next to a ruler so I could calibrate the distance. Then I imported the video into Tracker and marked the position frame by frame. And after that, I built a computation model in GlowScript using the provided starter code. And finally, I transferred both the datasets into Excel to compare the experimental and theoretical results. As you can see from Tracker, I determined the line of best fit for position versus time. The slope of that line represents velocity, the change of position over the change in time, which came out to be about 0.262 meters per second, and the y-intercept represents the initial position, or error in this case, which was about 0.0256 meters. The total time analyzed was about 1.77 seconds, and since the graph is very linear, that confirms the motion was approximately constant velocity. I then used these values as the initial conditions in GlowScript, and I set the net force equal to 0 to represent constant velocity motion. I entered the initial position and velocity that I got from Tracker into the code, and the time step matched the video frame rate, so the simulation progressed consistently with the recorded motion. But because the net force was 0, the velocity stayed constant and position updated linearly. So here I'm comparing the experimental data to the theoretical model, and as we said earlier, since both lines are nearly identical and follow a straight trend, that tells me that the model accurately represents the real motion, and any small differences between the two are likely due to tracking position, slight friction, calibration uncertainty, or just small timing inconsistencies. But overall, the agreement supports the assumption that the net force acting on the marker was approximately 0. As I said earlier, some possible sources of error include human error and friction air resistance acting against it, which caused um, the experimental line to sort of curve out, indicating the velocity was decreasing over time, meaning there was a external force acting on the system. But overall, the graphs were very similar. And if the axes were flipped, the position values and velocity would just change sign. The graph would still be linear, and the motion would still represent constant velocity. Basically, the physics would not change, only the direction we define as positive changes, and the net forces would still be 0. So the conclusions, basically, the marker moved at approximately constant velocity, the position versus time graph was linear, and the computation model matched the data and our experimental values closely. And since acceleration was 0, the net force was also 0, supporting Newton's second law in the end. Thank you.